Before we actually go ahead and calculate Q and W for specific chemical reactions, we need to understand one more idea about thermodynamics, which is this idea of state functions and path dependence. And so what we're trying to calculate here is the delta, right? Or the change in internal energy, delta E. As you'll see later on, we would actually be interested in calculating delta of other components as well. So the complication with calculating change or delta depends on the type of property that we are studying. So it turns out that there are certain properties, which in thermodynamics we call functions, right? There are certain functions that are what we call state functions, where if we want to calculate its change, all we need to do is figure out where it starts from and where it ends. So it's just the initial and final state. We don't need to know exactly how it goes from initial to final. All we need to know is just what's the value at the beginning, what's the value at the end. So that's really easy, right? So things like temperature, for example, is a good example of a state function. Don't need to know how it goes from 20 degrees Celsius to 80 degrees Celsius. All we need to know is it's 20 and then it's 80, okay? Some functions, we call them non-state functions. You need to know exactly how it goes from the beginning to the end, okay? So let me show a visual example here. Let's say you're hiking and you're trying to go from this initial state right here at the bottom of the valley all the way to the top right here, or midway through the top. That's your final state, okay? Now think about this here. There's two different paths you can take. You can take the path that's been paved. I mean, you'll eventually get there. Or you can sort of walk across or hike across. Or you go through this hilly part that's not paved. You're gonna get there as well. You notice that if I want to calculate the amount of time I have to spend traversing one path versus the other, that's not gonna be the same, right? The distance I travel, distance is just measured by how much meter or feet that you actually have to walk across, right? That's going to be different depending on whether you take path A, which is the cut across path, or path B, which is the paved path, right? So you can see that there's certain things that depend on path, okay? Where the value of it is not always going to be the same, even though you start from the same initial state and ending on the same final state. Now, what doesn't change here is the altitude that you travel. You're going to go from the altitude of, let's say, 0 here to the altitude of, let's say, 1,000 feet. So the altitude change is the same whether you take path A or path B. So the altitude change is going to be your state function. The distance you travel is going to be your non-state function, because that depends on the path that you take. So in thermodynamics, we have the same type of situations. We have certain things that are state function, like internal energy is a state function. We have certain things that are what we call non-state function or path-dependent function, which means that the value of that function or that property will depend on the path. Work and heat both are non-state function, okay? You can see this by just talking about moving object. If I move a book from the floor to the bench. There's many different ways to do this, but the two different ways that we're going to consider is, in one path, I would just take the book and put it on the desk immediately. Another path, I can take the book, walk around my house or my apartment, and then later on put the book on the bench. The altitude change or the height change of the book doesn't matter whether I do it directly or indirectly, but obviously the amount of work I put in is going to matter by quite a bit depending on the path that I choose. So this is something that we would need to think about a little bit more. This picture here is just sort of highlight the difference in work that you would do if you were to do it one path versus the other path. And you can actually calculate this. We're not going to go through that in this class, but it's something that you will go through more if you take a physics class. Now, what's the importance of the state function? Well, it's a lot easier to calculate delta or to calculate change if you're dealing with state function, because you don't need to know the specific detail of all these paths that you have to take. If somebody tells you that, hey, I got from altitude 0 to altitude 1,000 feet, okay, and that's all you need to know, that's great. That minimizes the amount of information or measurement I need to do. But if you need to figure out exactly how that person gets from A to B, it's going to take a lot more measurement to be able to do that, to get a lot more detail out of it. So having a state function is really convenient because that allows you to be able to calculate things without needing to know the exact detail. All you need to know is that you're starting from some beginning state and you're ending at some final state. How it gets there really doesn't matter. Choose any path I want really doesn't matter because the value is going to end up being the same, because all I'm doing is taking the final value minus the initial value. This is something that we'll talk a lot more about later, nearing the end of the chapter when we talk about Hess's law, because that's really the concept that underlies the use of Hess's law. Now, there are certain functions, as you'll see later on, that would be state function. And knowing that their state functions allow us to calculate their change or their delta just by taking the final value, subtracting that with the initial value. We don't need to know the path. Summarizing a little bit here, we're interested in calculating delta E, right? Delta E for a given reaction. The way we're going to do that is by figuring out how much in that chemical reaction, how much of the energy is transferred through heat and how much of it is that. We can calculate it, as you'll see in the next set of videos. How much of that energy is transferred through work? And again, work is something we can calculate mathematically. When we add those two numbers together, we're going to get our delta E. Delta E, it turns out all you need to know is just the beginning and the end. We don't need to know how the reactants become product. All we need to know is we have reactants, we have products. Just take the difference between those two numbers, okay?